Good morning, everybody. I'm so delighted to be here. There's so many friendly faces in the audience that I haven't seen in a very long time, so I'm happy to be here. As he said, the title of the talk is A Planet for Goldilocks. When I was walking down the hall, somebody said, "Are you looking for Goldilocks?" I said, "Yes, I am." Humanity, NASA, through NASA primarily, as was one of its conduits, is on a quest to find evidence of life beyond the solar system, right? And there have been many ways of doing that. I mean, you can go out and search the solar system, right? Maybe there was water on Mars once upon a time, so we might dig for fossils there. We might burrow down underneath the ice of satellites like Europa and Enceladus. Another approach is the SETI approach. This is too loud, sorry. The SETI approach, of course, is to listen for radio signals that are not naturally occurring, right? Evidence of technology. But what really has come center stage over the last few years is the search for life through the study of exoplanets, planets orbiting other stars. And the idea is that you look for the cradles of life, cradles of potential life, as we know it. And so we're on a search for this planet for Goldilocks, a planet that is just right for life as we know it here on Earth. This is a cartoon from XKCD, which we all know and love. I love to show this because when I saw this cartoon for the first time, I didn't appreciate what this sample of exoplanets that had been discovered as of June of last year really looked like. Every circle that you see there represents one of the confirmed, characterized exoplanets that had been discovered to date. And in the very middle of that square, of that circle, is a square that has a gray background that shows the solar system planets. And of course, the two largest there in the middle are Jupiter and Saturn. And so just scanning your eye over this cartoon, it really drives home the point that most of the planets we had discovered to date were larger than Jupiter and Saturn. And in case there's any observational bias here, because, you know, the small points, after all, are hard to see, I actually went to that date in the exoplanet archives and pulled down all of the known discoveries. And indeed, slightly over 50% of the planet discoveries were larger than Jupiter. And that's not what we're after, right? We're after something that looks more like Earth. Oh, and I'll just mention, this cartoon is actually quite well known. I gave a public lecture in New York just a few weeks ago to a relatively large audience, but I showed this cartoon and afterwards somebody came up to me and he was actually wearing a t-shirt with that exact cartoon on it. That was impressive, so I took his picture. I should have included it here. So Kepler is one of these steps towards this objective of finding life beyond the solar system. And Kepler has a very specific job. It's setting out to answer a very simple question, which is what fraction of stars in our galaxy harbor potentially habitable Earth-sized planets? And habitable, as I'm sure you're aware, means in the habitable zone, right? The distance between the planet and the star where the energetics are such that liquid water could pool on the surface of that planet, given certain reasonable climate conditions, right? So Kepler is detecting planets via the transit method, which is very different than the way that most of the ground-based planet detections were discovered. Staring at a large number of stars, measuring their brightnesses in the hopes that there are some whose alignment is such that the planet as it orbits the star will cast a shadow out into space that will sweep across our telescope. We measure the brightness of the star and perceive that event, that transit event, as a momentary dimming of light. So we're collecting images that look exactly like this. This is real data, pixel data, zooming in, going from left to right. And so we get these pixels, measuring these voltages on a CCD, which tell us something about the incident light. We turn those pixels into brightness measurements that have very high precision, about 20 parts per million for a G-type star orbiting a 12th magnitude G-type star. So, you know, we're not like Hubble. We don't get beautiful images that we can share with the public. We have to, in order to communicate our science, we have to really work hard to make the discoveries come to life. We don't often give public lectures and show light curves or brightness measurements as a function of time, right? We're going to get a lot of yawns. All right, so a planet for Goldilocks. You know, there's a plethora of planets out there. As of now, there are something like 900. We're quickly approaching 1,000 confirmed planets. Those are characterized planets. And so we see a huge diversity, and Goldilocks is there scratching her head saying, okay, well, what is going to be Earth-like? What are we going to define to be Earth-like or potentially habitable? And so it's really just simply two criteria: the size, not too big, not too small. The idea is once a planet core reaches a certain size, it becomes very efficient at accreting on the primordial hydrogen that's in that parent envelope that created that star and created its planetary systems. So that would be a giant planet like Jupiter. If it's too small, like Mars or Mercury, it's not going to be able to hold on to an atmosphere, and that's not going to be conducive to life as we know it. So size plays a role. And as I said before, also temperature plays a role. The idea, not too hot, not too cold, just right. And really what we're doing now is we're looking at the energetics, we're calculating the distance between the planet and the star, and then getting the star properties in order to estimate how much flux is being intercepted by that planet at that distance. And that energy tells us something about what the surface conditions might be. And granted, we know nothing about the atmosphere, right? And atmospheres can be warming, greenhouse gases. They can also be cooling, like water vapor clouds can be cooling. You can block radiation from reaching the surface. So you have to consider all types of scenarios in order to say something reasonable about what the conditions for water might be. So Kepler measures two things. The amount of dimming that happens during this eclipse event is directly related to the ratio between the surface area of the star and the surface area of the planet. So we get the radius of the planet by measuring the dimming of light, assuming that we know how big the star was to begin with. Here in this cartoon on the left, we've got a disk that's the size of Jupiter. On the right, we've got a disk the size of an Earth. So it's a 1 part per 10,000, or 10,000 to 1 is the ratio of area between a star like our Sun and a planet like our Earth. And that dictates the precision that we need. So we measure the size, and then of course we measure the orbital period, the time interval between the dimmings of light. That tells us, according to Kepler's empirical laws, modified by Newton, of course, that tells us how far away the planet is from the star. And that tells us the energetics. So it's very simple science. I mean, the beauty of this mission in dealing with the public and as an educational tool, the science is extremely simple and illustrates physical concepts that we teach both in an Astronomy 101 type of class, but also in an introductory physics class. So it's a nice way of showing the applicability. What I'd like to do is kind of give you the bird's eye view of what Kepler has discovered so far, and I'd like to put it into context with all of the exoplanet discoveries that have been made to date, not just by Kepler, but by all teams. And so I'll do that through a scatter plot of size versus orbital period, both of which are on a logarithmic scale. I put some horizontal lines for comparison: Earth, Neptune, and Jupiter. And I'm going to fill in this plot with various discoveries. If a discovery was made by the Doppler method, it will be colored pink. Transiting planet discoveries will be colored light blue if they were not discovered by Kepler. And then at the end, I will add the Kepler discoveries in yellow. Now, this is a little more tricky than it might seem, because a lot of those early discoveries, as you know, and even today, were made with the Doppler method. And the Doppler method tells us something about the gravitational tug, right? Because you're looking at the Doppler wobble. And that's going to give you the mass. So Kepler measures the radius. It's the amount of dimming, right? So those are two very different quantities. We're comparing apples and oranges, and you have to be able to kind of work back and forth if you want to make a reasonable comparison. And we can't really honestly do that very well. But what we can do is we can look at our solar system planets and plot their masses versus radii and fit some kind of a polynomial, some kind of an analytic function that maps one to the other. And that does a kind of a reasonable job. And so that's what I've done with all of the Doppler detections. I've used this polynomial fit for the solar system planets to take the mass of the Doppler discoveries and convert it to a radius, and that's what I'm showing you here. Okay? So we start in 1995 with that lone pink dot, which is 51 Peg, that was announced by Michel Mayor in 1995 at a conference in Florence. I was a graduate student at the time and just happened to be lucky enough to be there. Didn't appreciate it at the time, its significance, but it was exciting nonetheless. And so now I'm going to tick it forward and I'm going to add in the other discoveries over the years, 97, 99. In 2001, we have our first blue transit point. We tick forward to 2009. This is the year that Kepler launched. So this provides us with a snapshot of the state of affairs right when Kepler launched. And so you see here statistically, you've got this pink swarm of Doppler detections at long orbital periods and planets that are very large, larger than Jupiter. And you've got this tiny little cyan blue swarm at very short orbital periods, just days, but also around Jupiter sizes. And then you have a smattering of points raining down at smaller sizes. Some of those were due to satellites like Corot. Some of them are Doppler detections. And again, remember that the conversion from mass to radius is very crude, very crudely done. So I'm going to tick it forward again to the present time, but I'm going to do so adding only discoveries that were made that are non-Kepler's discoveries. So 2009, 2010. 2011 and 2012. So that gets us almost up to the current time. And the statistics didn't really change that much. In this snapshot, 85% of the planets in terms of mass are larger than Neptune. Most of them are above that line. You still have the two swarms of giant planets, one for the transiting and one for the Doppler. And now I'm going to show you what Kepler has discovered after analyzing 2 years of data. The mission launched 4 years ago, and in fact has already completed its baseline mission. It's not currently operating. I can tell you more about that at the end. But it did complete its baseline mission, and in fact took another 6 months of data beyond that. But of that 4 years, we've analyzed the first 2. So the points I'm going to show you are after having analyzed approximately half of the data that we have in hand. Right? So this is what it looks like today. So you can see that Kepler has made an enormous contribution to exoplanet science, really completely changing the demographics altogether. The statistics that you were seeing before, whereby 85% of the planets were larger than Neptune, was an observational bias, right? Due to sensitivity. We've got this new piece of technology now that's up there in space, taking data in a new way with very high precision that's never been done before, and that cracks open the field, right? And so now, instead of 85% of the planets being larger than Neptune, we have 85% of the planets smaller than Neptune. As I said, it's difficult sometimes to communicate to this public in an exciting way. We've got these pixel values that we get in the upper left-hand corner. This is an example of what the data actually looks like. Every white point there is a brightness measurement, and you see this very shallow 1 part per 10,000 dimming of light, a little bit more than 1 part per 10,000. This is due to a planet that is about 40% larger than Earth. And so we learn from this. We learn the radius, we learn the energetics, as I told you, the orbital period and how far away it is from the planet. But then oftentimes we do ancillary follow-up observations that tell us even a little bit more. For this particular planet, we also learned its mass through spectroscopic observations with a Keck 10-meter telescope. But the point is that we take everything that we learn about a planet, we do some theoretical models, and we give all of this information to artists. And then the artists render these worlds and try to make them come to life. And that's what you see in the bottom right-hand corner. So some of that is just flight of fancy, some of that is imagination, but it always impresses me how much of it actually comes from what we know. So it's not just random, pretty pictures. So with that, I'd like to show you, introduce you to some of the personalities, some of the worlds that are kind of like, they're becoming like destinations, right? We know something about them, it's starting to feel personal. The first one is Kepler 10b. You just saw its light curve. I call this a lava world, or scientists are calling these lava worlds, because they are orbiting very close to their parent star. Kepler 10b is 23 times closer to its sun than Mercury is to our own. So one entire hemisphere of this planet has temperatures in excess of that required to melt iron. You're going to have an ocean larger than the Pacific Ocean. This planet is 40% larger than Earth, but it's an ocean of lava. Kepler 10b is not the only rocky planet that we know of that's around the size of the Earth. As I mentioned before, this planet has a mass, so we have a mass and a radius. And with mass and radius, you can calculate density, right? The average density. So we know that this planet is something that's rocky. It has a very rocky composition, very high density, something like 9 grams per cubic centimeter. And it's not the only one that we now know of. There are a few others. Another system, Kepler 36, has a planet slightly larger. And its mass was determined not from the Doppler wobble, but by dynamical models looking at the timing of the transits, observing that the orbit is not perfectly Keplerian. The orbit is being perturbed by the gravitational force of neighboring planets. And so by looking at the exact nature of those perturbations, you can apply dynamical models that then tell you the mass. And in that case, it was done with very, very high precision. So these rocky planets are beginning to appear and become characterized. So far, none of them are exactly like Earth, but maybe we can say that they are by analogy, which I'll show in a second. We've also learned that there are planets that orbit multiple suns, finally proving that George Lucas was right, which was exciting. This is Kepler 16b. And so these two stars are in a very tight orbit, orbiting one another and eclipsing one another. So you would see those two stars not just rise and set, but also swap places as they orbit one another. And these are called circumbinary planets because they are orbiting both of the stars, not just one, in a very wide orbit. We've got several of these. We've also seen planets orbiting stars in star clusters. There are 4 open clusters in the Kepler field of view. This one in particular that's being depicted by our artist's rendering is 1 billion years old. It's NGC 6811. And here the artist has imagined what the night sky might look like from this planet, given the fact that you have a significantly higher star density in this cluster environment. We've found planets that are just the right size. Kepler 20e and 20f are examples of this. This Kepler 20 is a 5-planet system. 20e is slightly smaller than Venus, and 20f is slightly larger than Earth. But they are in also very tight orbits, one orbiting with a period of just 6 days, and the other orbiting with a period of about 20 days. So they're going to be too hot. These are not Goldilocks planets. We also see planets that have just the right orbit. Kepler 22b, for example, is one such example. It's orbiting a star that's slightly cooler than the Sun in an orbit of 289 days. So it's very, very similar. It's receiving a very similar amount of energy compared to Earth, but it's larger. In this discovery paper, it was pinned down at 2.4 times the size of the Earth. And so at that radius, you hear in the media likes to report a super Earth was discovered, and that invokes these images of something rocky but bigger, lots of real estate. And in fact, the theoretical models are saying that no, it's probably not like that at all. It's probably more like a mini Neptune. So those are two very different things, right? Super Earth or mini Neptune. Mini Neptune implies that it has an envelope of volatiles, hydrogen and helium-rich molecules, providing some kind of a liquid or gaseous or icy envelope. So it probably doesn't have something that's rocky like Earth. However, I'll just give you a little tidbit. Recently, there's been a re-evaluation of the data that told us how big the host star is. And this was done by astroseismology, by detecting P-mode oscillations, acoustic oscillations coming from the star itself. So just like seismology probes the interior of our planet, acoustic waves propagating through a star can tell us something about the fundamental properties and interior structure of a star. And you can see evidence of these acoustic oscillations in the Kepler data. And we use those when we can see them with high enough signal to noise, we use those to get the fundamental properties, which allows us to get the fundamental properties of the planet very, very well, with very high accuracy. Except in this case, the oscillations were very low signal, so they didn't have a lot of statistical significance. And now that we've got significantly more data, the oscillation spectrum has really lifted out of the noise, and the radius has been revised. And it looks like this planet is actually more like 1.8 or 1.9 times the radius of the Earth. It's getting smaller. And most recently, in April of this year, we announced the discovery of the Kepler 62 system, another 5-planet system. This is a K-type star, about 1,200 light years away, and you've got these 3 inner planets, one of which is only the size of Mars. But out in the Goldilocks zone, shaded green, you've got Kepler 62e, which is 1.9 times the size of the Earth. And then we'll swing right out to Kepler 62f, which is 1.4 times the size of the Earth in a 267-day orbit around this early K-type star. Remember, well, we don't have the mass of these, right? We don't have a Doppler signal. They're so far away that the tug is going to be too small to detect with current technology. Nevertheless, remember, Kepler 10b, our rocky planet, our lava world, was also 1.4 times the radius of the Earth and is known to be rocky. The same with the Kepler 36 planet, 36b I think it is. So it is very possible that this is a rocky planet at this radius, this same radius, 1.4 Earth radii, and it is in the habitable zone around a K-type star. So Goldilocks there is pretty happy. This is a schematic of what that system looks like compared to the solar system. And so looking at a diagram like this, it's very easy for a student to make a comparison and see just the diversity of systems that are out there. Not everything looks like our own solar system. We're learning so much. The Kepler 62 system is much more compact. Its habitable zone is tighter. That's because the central star is a weaker campfire, right? It's a K-type star. So you have to cozy up next to it in order to get the same energetics compared to our solar system with the central star that's hotter, our G-type star. You can see the range in sizes compared to the solar system. That tiny planet 62c in that inner orbit is only about the size of Mars. So we're seeing very, very tiny signals, albeit not in the habitable zone, but even planets like Mars and even Mercury we have seen. Okay, well this is great. All of these nice worlds, they're sounding like destinations, and we're excited, and I'm sure they're going to be characterized for decades to come. But really, Kepler is about statistics, right? We want to know the frequency of these planets, the prevalence of these planets in our galaxy. So this is just a simple bar graph. I didn't tell you the number of yellow dots that were in that previous plot, but there were over 3,000. I think the current count as of today is something like 3,700, somewhere around there. These numbers don't add up to that because they're based on an earlier release, but the general behavior of the bar graph still looks about the same. At these orbital periods that we've probed so far, which are short, right? Maybe Mercury's orbit and inward, because we haven't yet analyzed the next 2 years of data. We're seeing that the Jupiter-sized planets are very rare, maybe perhaps not surprising, because we're within the ice line. But the super-Earths and the Neptunes, even Earth size, are quite common. But what do we do with a bar graph like this? How do we take this and go from this to a statistic, to this number that we want to compute, the fraction of stars that have Earth-sized planets in the habitable zone in our galaxy? This adds up to maybe something like 3,000. We observed something like 150,000 stars. So can I just say, well, 3,000 out of 150,000, what is that, 2%? Is that the answer? 2% total, maybe even smaller for the habitable zone planets? And the answer is no, right? Because not all of these stars have exactly that right alignment. You know, that in fact the probability of that having that alignment is very tiny. It's like 0.5%. So for every one we saw, there's like 100 or 200 others out there that weren't in that proper geometric alignment, right? We have to make those corrections. That's one of the observational biases, and there are a few others that we have to correct for. So we do that as best we can, and a few people have already published this in the literature, and here's an example of one such histogram. You can see that those corrections have even further suppressed the giant planets and further elevated the tinier planets. And in fact, the Neptune, super-Earths, and Earths almost look like a flat distribution. And then it just plummets as you go to the gas giants there on the right. Keeping in mind that this is for orbital periods less than about Mercury's orbital period. So from this we can see certain statistics. The fraction of stars with at least one planet are these different percentages, 15, 20% for these small planets. And then the question becomes, okay, well, this is over all orbital periods less than 85 days. Is there anything we can say about the prevalence of habitable planets at this early stage? Those 3,000 points that I showed you, I've put together this plot, which is a little bit more complicated. It's got a lot of information here. Instead of plotting orbital period on the x-axis, I've plotted the stellar flux at the planet's orbit. So this tells us how much energy is being received by a given star at that distance, okay? And on the y-axis, I'm actually plotting the surface temperature of the star itself. It's kind of a funny, non-intuitive way of plotting this. But every single point that you see there is one of Kepler's planet discoveries. And then you see this green shaded region. And that green shaded region is the habitable zone. That's the place, that's the flux at which a planet could have liquid water pooling on its surface. And so you've got a series of tiny gray points that fall within there. And then you've got some bigger green points that fall within there. All of them are Kepler planet discoveries, but the green points I emphasize because those are the planet discoveries that are smaller than twice the Earth's radius. And I scaled them to the size of the solar system planets. Let's see, I don't have a, is this also a, no. Up here, around 5,800 degrees Kelvin on the y-axis, you can see a horizontal line of planet images, Mercury, Venus, Earth, and Mars. Thank you very much. Let's see, Mercury is hiding right here someplace, right there. Mercury, Venus, Earth, and Mars. And so these green points are to scale with Earth. All right, so this one is about the size of Earth, and then these are up to twice the size of Earth. I've got some others that are in here, like this big one right here is Kepler 22b. These two are Kepler 62e and f, orbiting a much cooler star, right, the K2 type star. Here is Kepler 69c, I think it is, orbiting a star that's almost the same temperature as our sun, and it's just on the inner edge of the habitable zone. But you can see that we have several candidates here that are smaller than twice the Earth's radius, but they're all orbiting stars that are cooler. They're K and M type stars, barring 62. We've actually recently, like within the last few weeks, added about 10 new discoveries in this space. They are also predominantly cooler than 5,000 degrees Kelvin. We really need to finish analyzing this last 2 years of data to start finding things in here. But what I want to point out is that these planets way down here orbiting the very coolest stars, 3,500 Kelvin, their habitable zones are going to be very close to their parent star, right? So the orbital period is going to be very short, within the 85 days that we are sensitive to. So with these few discoveries down here, it's already possible to say something about the prevalence of potentially habitable worlds based on a small number of planets. And so, well, this just illustrates, just to drive home the point, that the M-type stars are so much less luminous than the G-type stars, and this makes their habitable zones closer in, something on the order of weeks to months. And also I wanted to show this schematic. This is all of the stars within the solar neighborhood that we know of within 10 parsecs. This is from the Recon survey by Todd Henry. And they're sized according to spectral type, A, F, G, K, and the M's. And here are the numbers in each bin. Over 70% of the stars in a volume-limited survey are going to be these M-type stars. So it's very interesting to make a first guess about the statistics of potentially habitable worlds around these M-type stars. And so when you do that, you can ask yourself the question, how close is the nearest potentially habitable Earth-sized planet likely to be? If you were to take the galaxy and scale it down to the size of the continental United States, and if you stand over there in Golden Gate Park, like on Ocean Beach there in San Francisco, and you look across the continent and you say, okay, where's the next potentially habitable Earth-sized planet going to be? And the answer is, it's just across the park, or about 15 light years according to the statistical study based on those small number of planet candidates. So it's not very far. Even though we have very few detections of these potentially habitable worlds around M-type stars, it's still indicating that they are going to be quite prevalent in the galaxy, that we don't have to go out very far to find one. And this was really great news for the next missions. Right? Already we are taking these numbers, NASA's taking these numbers and starting to use them to justify future missions. And so with some of the time that I have remaining for about the next 10 minutes, I'd like to tell you a little bit, give you a feel for what comes next in this search towards finding evidence of life beyond the solar system. What we want to do is we want to go from a habitable zone to a habitable environment, right? We want to, it's all well and fine to know that a planet is in the habitable zone, but that doesn't tell you if it really is a habitable environment, right? So ideally, we'd like to see an image like this of another world, but it's going to take us a while to get there. One thing that you want to do first is you want to see if there is evidence of water. Here's a spectrum of, a model spectrum of Venus, Earth, and Mars. On the bottom is the optical. You can see the optical region. And so going to the right, you're going into the near IR and the infrared. And you see the different features in each of these spectra. The Earth spectrum looks characteristically different than the spectrum of Venus and Mars, and has those water bands, oxygen bands, the very strong water bands in the infrared, but also in the near infrared. So you'd want to look for evidence of water. That would tell you that it is truly a habitable environment. One way to do that is through transmission spectroscopy. These planets that we know are transiting their host star will have some of the starlight filtering through the atmosphere during that transit. Here's an image of Venus transiting our sun, and you can see this very faint yellow line just hugging the surface of the planet. The scale height of that atmosphere is like 5 kilometers. It's very tiny. So this is very, very difficult to do. Already, we saw that a transit of the whole entire disk of a planet like Venus is like 1 part per 10,000. And then you're taking just the 5 kilometer scale height. So this is extremely difficult to do. I've read in the media a lot of scientists saying that JWST, the James Webb Space Telescope, is going to do this. It is not thought that James Webb Telescope will have the capability of probing the atmospheres of Earth-sized planets. However, it will be able to do it for some of the super-Earths, maybe the mini-Neptunes. It will be able to help us to disentangle the difference between a super-Earth and a mini-Neptune. So that's what we're shooting for with JWST, that intermediate step. But JWST will only be able to do that for the closest, brightest of stars. Kepler is not probing the whole entire sky. Kepler is focusing on one patch of sky near the plane of the Milky Way galaxy that's about 100 square degrees, or the size of my hand, my open hand. And it's probing out into the galaxy about 3,000 light years because it's trying to build up statistics. If you want to find all of the planets that are closest to the solar system, everything that's in do a census of the solar neighborhood, that's a different kind of mission. And I'll talk a little bit more about that in a second. So we really need that different kind of mission to be able to find nearby objects that JWST can then characterize. But besides transmission spectroscopy, we could do the same kind of thing, watching light not transmit through an atmosphere, but scatter off of an atmosphere. And on Friday, how many of you waved at Saturn? Oh, that's pathetic. Serious? Not even half? I'm ashamed. This was, it's an iconic image, right? This is what they sought to do again, to repeat last Friday. Taking advantage of the fact that Saturn, the disk of Saturn, is occulting the sun, thereby pulling out structure. You get the scattered light through the rings, of course, which is just gorgeous. But you also get to probe the environs, and you can see the pale blue dot, which is Earth. Harkens back to Sagan's pale blue dot from the Voyager spacecraft. And there it is blown up on the left. It's a smudge. It's a smudge of light taken from Cassini, which is right up on top of it, right? I mean, we're in the solar system. Imagine trying to do this for a distant star, a distant planet orbiting a distant star, right? It's significantly more challenging. But the idea is the same. You have a technology that suppresses the starlight so that you can see the faint environs, so you can see that firefly in the glow of the searchlight. Right? This happens to be a very good, very excellent star shade. Actually, it's the wrong shape. The current idea is that the star shade that would be used if it's an external occulter as opposed to an internal coronagraph. An external occulter would be some kind of a large screen that we would fly at some distance to perfectly block out the starlight. And that helps make the wave control optics of your telescope a little bit simpler to have this external configuration. The thought is that the shape of that occulter is going to be more like a sunflower shape. It has petals in order to minimize the central bright peak due to diffraction. But that's just an aside. So you can see this little smudge here. It's not resolved. We can't see continents, we can't see an ocean, we can't see evidence of forests, but we do have this disk-integrated light, and you can imagine putting it through a spectrograph and looking at the colors, trying to find that pale blue dot and maybe other features from the spectrum itself that say something about the whether or not that's a habitable environment. And so this is basically NASA's roadmap to get us to through the next 30 years or so. Kepler is there. It's the third mission there, coming up from the left. I mentioned that we want to then find all of the nearest planets, and that would be a mission called TESS. TESS has already been selected for flight. It's an Explorer-class mission. And TESS is going to find planets exactly like Kepler finds planets, but it's going to do so surveying the whole entire sky. So it's only going to stay on one patch of sky for a short amount of time, weeks to maybe a couple months, and then it's going to move. And it's going to keep doing that patchwork style until most of the sky has been covered, focusing on the nearest objects. Again, the idea is to find the edge-on systems that are closest to us. In doing so, it will find a sampling of these super-Earth mini-Neptunes that can then be observed by JWST, which is the mission right after TESS. After JWST, looking forward a little bit more into the future, there's something there called AFTA. I've forgotten what AFTA stands for, but this is also a statistics mission. The name on the books is WFIRST. It's a combined cosmology, dark energy, exoplanet mission. And what WFIRST, or AFTA, is going to do is to complete the statistics like Kepler started, right? Kepler is looking at statistics of planets that are within 1 astronomical unit. Now we want to probe things that are beyond the ice line, get the statistics of things that are beyond 1 astronomical unit, and that's what AFTA, or WFIRST, is going to do. It was actually just recently approved by NASA, the use of a 2.4 meter mirror that came from the National Reconnaissance, classified military use. They repurposed it and gave it to NASA, and that telescope, that mirror, is going to be used for WFIRST. So it is already baselined. There are science definition teams that are going forward with the planning of that mission. And again, that will complete the statistics out beyond the ice line of the perhaps giant planets like in our own solar system. So now we'll have a complete set of statistics about exoplanets. We'll have started to characterize some of their atmospheres with JWST and the planets that TESS finds. And beyond that, in this very faint, barely visible, grayed out region that's kind of 30 years down the road, is this thing called the New Worlds Telescope. And this is the mission that is going to image the nearest systems, looking for these pale blue dots whose spectra we can take to start to find truly habitable environments. Beyond that, there is also a roadmap, and that roadmap is to find a true blue marble, to take an image that's resolved so that you can actually find oceans, evidence of a forest, for example, vegetation. You can take resolved spectroscopy. This is going to require very large baseline interferometers, but the point is, even though this might be 50 years plus down the road, it is being implemented. It is being planned. There's technology development going on right now. So this is the near future. Being able to take an image of a beach on another planet is in the relatively near future, right? So this is not, when I come and say that we are on this quest to find evidence of life beyond the solar system, this is not science fiction. This is not something that's just fanciful. This is something that we can really have a dialogue about. And so this represents a very, very unique time in science, and as educators we can leverage that because it's generating a tremendous amount of excitement that we can bring into the classroom and use to teach science, technology, mathematics. This is a very famous image that was on the cover of, I want to say, Nature magazine. And this is a microscopic image of cyanobacteria. When cyanobacteria metabolizes, it creates a gas. That gas is oxygen. We believe that the oxygen we observe on planet Earth today was created early on by these microbes, these primitive, earliest life forms here on planet Earth, these cyanobacteria. So if you have a resolved image like this, and you can take a spectrum of that, you can start to look for these signatures of molecules that we know are produced by life and try to understand that chemistry. So this is why finding evidence of life beyond the solar system, I believe, is in the near future. All right. I want to point out just a couple of resources for educators related to Kepler and exoplanets in general. This report, this compilation of educator resources for exoplanets was just released, I think, last week. Andy Fracknoy compiled this. It's on the astrosociety.org website. It's excellent. It's got just about everything in there imaginable, from websites to popular books, to videos that are online, to apps. The Exoplanet app is mentioned, to citizen science. Many things are in there, and so I won't try to give you an overview. You have this at your fingertips, and I encourage you to look at it. But I thought to myself, what could I share with you that might not be so obvious to try and help you in the classroom? So I wanted to point out just a few things. The first thing I wanted to point out is that we actually have two websites. Kepler has two websites. It has an EPO website, which is kepler.nasa.gov, and it has the NASA website, www.nasa.gov/Kepler. They are both useful in slightly different ways. The EPO website is useful for multimedia. It has some pull-down tabs at the top. One of them is called Galleries. right here. I don't know if you can read it. Galleries. And in those galleries, you can get all of the multimedia resources. However, I will caution you that I have found it very challenging to find what I'm looking there. Instead, what I recommend you do is go to the News tab, because there's a Kepler in the News pull down here that lists every single discovery or press conference we have ever had. And if you look at the ones that you're interested in and you follow those links, you will not only get the images and animations and videos, you'll actually see the PowerPoint files that were used in the press conference itself, which are very well done, well thought out, very carefully thought out for exactly a GE kind of audience. The other thing I wanted to point out here is the Education tab. This compiles a list of education tools, formal education, informal education, outreach, amateur astronomy, you name it, it's there. Poetry, music, art is listed there. A ton of resources there on this EPO website. The NASA website, on the other hand, is your one-stop shop for recent news. You saw something in the news, you know that a new discovery has been made, this is where it's going to hit first. This is where it's going to be published, because the NASA portal itself at www.nasa.gov gets a very large volume of attendance. So when we put out press releases, they go here first. There is another very, very important resource that's relatively new in that it's growing a lot, and I don't think I saw it in the Educator Resource Guide that was online, so I'm mentioning it here. This is the Exoplanet Archive. This comes right out of the NASA Exoplanet Program Office. The NASA Exoplanet Archive is supposed to be, the vision is that this is a one-stop shop for all of exoplanet data. And so we've got all of the Kepler catalogs are there, all of the different planet catalogs are there. You can peruse them. They also have generated, they have a page where you can get these kind of pre-generated plots that give you a snapshot of the current state of exoplanet research at any given time. So that's useful. If you go to one of these catalogs, maybe Confirmed Planets or the Kepler catalogs, you get these tables that have lots and lots of parameters that you can pull up. You can download them in ASCII format. You can search them based on certain characteristics you put up at top. You can plot the table, various quantities, and you can set what a GUI pops up, and you can set exactly which characteristics you want to plot, and it gives you a nice plot. You can plot against logarithmic or linear scales. You can do lots of different things. Also, back on this page, if you click on the Information tab, it gives you a whole nother set of websites with additional information, one of which is the time series data itself. And so if you click on that time series tab, it'll take you to a page where you can choose which data you want to look at. You can change the range. You can fold the data. You can plot it as one continuous long time series, or you can fold it at the orbital period to see the transit events themselves. And all the tools are up here on the tab. There's I think on a previous slide I showed this publication by Rachel Akeson. It just came out. It's on AstroPH and explains in gory detail all of the intricacies of this exoplanet archive. And she shows examples. It's a tremendous resource for you if you want to have the students, like in a lab class, play with the data itself. Okay. There's another website at keplerscience.arc.nasa.gov. This was the previous home of the Kepler Guest Observer Program, and it has morphed now into just a general, kind of a technical science center, but it has lots of tools for analyzing data, tools that are written in Python, for example, if you have upper division students that want to do research. But I wanted to draw your attention to one cool thing. Under Tools is a link to Google Sky, and it gives instructions for pulling up the Kepler field of view on Google Sky. So if you use Google Sky in your classroom, you can actually show the Kepler field of view in the summer triangle there. Another fantastic resource is, of course, the citizen science sites. This is planethunters.org, powered by Zooniverse. And it's a site that serves the public light curves and asks some very simple questions about the behavior or the appearance of those light curves. So, for example, is the star, and then it gives you these, if you mouse over these different choices, it tells you what to look for. Is it periodic? Is it randomly varying? Is it some kind of a stochastic variable? You choose them. You can stretch the data in and out on this bottom bar. And so you quickly get very familiar with Kepler data, but you're also doing them a favor. You are using your pattern recognition tools to sort all of these light curves that Kepler has. And so they've got tens of thousands of people who are doing this all the time. They have characterized literally billions of light curves in this way. And some of these citizen scientists who are doing this have actually gotten their names on publications. They've contributed to discoveries, to actual discoveries of new planets. So that's very exciting because it gives the layperson direct experience with the scientific method, right? Which I know for me was very, very important in understanding what science is all about. Besides just characterizing the light curves, they have a very nice interface for discussing them, sharing information and impressions. So they've got this whole blog site that's very well integrated by the different targets. People can chat and talk about them and share information. We've had Kepler scientists go to this page to look at all of the information that in this chat window to see what people have learned about these objects. I'd like to circle back to Goldilocks. I know that the theme of this workshop is STEM literacy. STEM literacy begins with Goldilocks' spirit that drove her into the forest to begin with, right? When I was a little girl reading the myth of the fairy tale of Goldilocks, I was really impressed by the fact that she went into the forest at all. That seemed scary to me. But it really is true that, there is something innate about all of us, this innate curiosity. And we have an increasingly large talent for squelching that curiosity. It seems to me that by the time our students are getting to high school and even college, a lot of that curiosity, innate curiosity, has been squelched. And so we spend a lot of our time trying to engage and inspire to make up for that. I think our test results for STEM that point to the fact that our STEM literacy is declining has responded by, we've responded by doing more earlier and doing more testing, which of course is going to create this cycle of squelching the innate curiosity even more. So that's the bad news. The good news is that we are in this age of really tremendous science that's getting done. The fact that we are on the verge of finding evidence of life beyond the solar system has not only scientific implications, it has deep philosophical implications that is engaging everybody in a dialogue. We have people who say, we can't find life. I mean, they're going to come, they're going to destroy us, we're going to destroy them. I mean, it's going to be chaos. And already I see this dialogue emerging that's kind of like when you invite your relatives over for dinner and you think to yourself, God, I better clean the house, right? And that's a positive thing, that's a good thing, this idea that we have to clean our house. So the dialogue that's emerging is not just scientific. It offers an opportunity for us to use their enthusiasm to teach science, but there's also a dialogue here about art, music, science, poetry, and philosophy. I gave a talk a couple weeks ago where they asked me to speak about the philosophical implications, and we got into a large dialogue about compassion. And I think that this is very important too, so if I can just end my talk on this one note. When the Apollo astronauts, we had the 44th anniversary of the moon landing on Saturday, when the Apollo astronauts turned back and took a picture of the blue marble, compassion grew here on Earth, right? Because you realize that from space there are no borders. When we teach our students that the atoms in our body come from stars, compassion grows, right? Because we realize our connectedness. And as we go out there and we search for life, and one day when we do ultimately find evidence of life beyond Earth, compassion's going to grow again. And so it's very important for us to have that dialogue, as uncomfortable as it may make us feel sometimes, especially as scientists. It's very important to include that as part of the dialogue, because that kind of dialogue is going to keep Goldilocks looking up, right? So with that, I will end, and I'm happy to take your questions. I think we have like 7 minutes for questions. Yes?
Quickly, I'll say thank you to the Kepler EPO. One other thing that's on the website is a way to build yourself a model of Kepler.
That's right.
And a little light detector and make planets. And we've had over 1,000 Astro 101 students make their own solar systems in Kepler, and they love it. It's their favorite lab.
Thank you.
The comment I wanted to make was, it occurs to me that M stars, they can be preferable to B stars to look for life for the following reason. Our sun is not the same sun it was 4.5 billion years ago. And one of the things we've struggled to understand is the sun is brighter now. It's, obviously not off the main sequence, but it's high. It should be higher, but it's tens of %. And so when you talk about life on the Earth, it's always been a struggle. And as the sun changes, do you still keep having life? M stars would evolve much, much less. And so the faint early star problem ought to be much less, I think.
That's a very controversial subject. I mean, our M stars also last a lot longer, right? They'll be the age of the universe, right? But there are other things, arguments against life forming on M dwarfs. The large amount of activity, they have very deep convective zones, so they're going to have a lot of magnetic fields, which creates, flares and the like, and perhaps that could have some negative impact on life. The other things that people have mentioned is the fact that the planets in the habitable zone are very close, and so might be tidally locked to their host stars, and so that's another consideration. So I don't know. It's going to be very interesting to find out. Yes?
In your slide where you were plotting the nature of the star versus plus, you had two green sections, one that was empirical habitable zone and one that was narrow habitable zone. Could you briefly explain what the difference is?
Yeah, the empirical habitable zone is based on what we know in our solar system, that the habitable zone is kind of between Venus and someplace beyond Mars, right? If Mars had been larger, it would have been able to hold on to an atmosphere, and it would probably still be habitable today, so someplace beyond. The empirical habitable zone is based on climate models that say, okay, let's just consider the most extreme atmospheric compositions. If you're really far from the star, you need a lot more greenhouse gases. Okay, so let's pile on the CO2 and let's see what happens, right? And so you do these extremes and you get this empirical, I forgot what I called it, but the narrow habitable zone. Yeah, exactly. So it's just, we tend to use the empirical just because, not only is it more optimistic, there's just so much we don't know, and to take these extremes and run these climate models and you don't know what uncertainties are associated with them, what systematics, what ingredients we do and don't have, it just seems more prudent at this point in the game to use the empirical habitable zone. But our ideas on that are going to evolve. We just started a new habitable zone working group who's going to track this very closely and probably also create a website that you can go to. It doesn't exist yet, but soon there will be a website you can go to where at any given moment in time you'll see all of the planets that Kepler has found that are in this habitable zone. Yes?
Kepler's been written off because you didn't really talk about it.
Yeah, no, I didn't have a chance to talk about it, that's right. So no, in fact, last week, well, let me tell the backstory. Kepler is not taking data. It had a failure of a reaction wheel. So Kepler had 4 reaction wheels, and they're basically gyroscopes that control the telescope's pointing, and that's part of the reason why we get very, very high precision with Kepler, because we're controlling the pointing so accurately. So we need 3 for operation. One of them failed last July, about a year ago. We were down to 3. There was another one that was showing signs of failing, some kind of friction spikes every once in a while that looked like it was sticking. And that reaction wheel failed on May 14th or thereabouts this year. So at that point, we stopped taking data. However, we've now developed a plan for mitigation, a plan for recovery, to try and see if we could maybe jiggle them, give them a kick, see if we can get them spinning again. We're not very hopeful that that will work, given what we've seen. It indicates to us that something is actually broken inside of the reaction wheel that's lodging it. Last week, however, we did our first test on the worst of the two reaction wheels. And we applied a torque in one direction and it didn't move at all. We applied it in the other direction and it started spinning. And we let it spin for 30 seconds and turned it off. And today, we're going to do the same thing with the second reaction wheel. The 30 minutes of time that we spun it, we measured the torque on that reaction wheel over that 30 seconds, and we're going to analyze that data and see how it performed. So all is not completely lost. It might be that we can get them spinning again, but we don't expect... We're not very hopeful that we're going to be able to take new data that will allow us to detect and discover more planets. But with that said, we're not sad about it either, because we've already got more data than we expected we would have, so it's all good. Yes, they're in the back.
How much more unanalyzed data do you have to work with?
About 2 years. So we've analyzed 2 years, and we have about another 2 years of data, in our back pocket. That was the last question, I've been told, so thank you very much for coming. I look forward to a great day.